Okay, so students, we have discussed that how is this displacement current additional term this Maxwell brought in order to rectify the limitations of the Ampere's circuital law. Okay, and I have also brought one example in order to explain this particular thing. Okay, now let us just write what is this epsilon naught and phi er. Okay, epsilon naught is, I'm writing here, epsilon naught is your permittivity of free space. Permittivity of free space. And what is this phi e? Phi e is your electric flux. I hope you have come across this term electric flux in your previous chapters. Okay, electric flux through Gaussian surface. I hope this Gaussian surface term also you have come across in your junior classes. And in the previous chapters also you have come across this term Gaussian surface, I hope. Alright, students. So, this equation Maxwell brought. Okay. So, if you just think, since this phi e is our electric flux through the Gaussian surface, so if we differentiate this phi e, so what will be, okay, I'm writing it here. If let us consider del phi by del t, that means differentiating electric flux with respect to time t. What will happen? It shows, that means this particular expression shows the rate of change of electric flux. It's very natural, think it in a mathematical way. Del phi e by del t means the rate of change of electric flux. Okay. So, this particular equation, I'm writing this particular equation once again. Okay. So this equation becomes, that means this particular equation becomes ID equals to epsilon E del phi E by del T. It's very obvious that two mu's which are there on both the equations will cancel each other. Alright. So this particular equation, I'm writing it as equation number 3. Alright. So this particular equation or expression represents the varying electric field, as I told you all. So this varying electric field is equivalent to the current flow between the plates of the capacitor during charging. Students, I hope in your previous class I have brought the example of the capacitor, the charging of a capacitor, isn't it? I'm just recalling it once again. What was happening? That when your capacitor was charging, so what will happen? The varying current will flow through the circuit, isn't it? But in actual, no current will flow in between the plates of the capacitor, isn't it? Now what will happen? After bringing this Maxwell's displacement current expression, what will happen now? This varying electric field will be equivalent to the current flow between the plates of the capacitor during the charging condition. Clear? This particular phenomenon is known as your displacement current. Alright. So just correlate between the two cases. What was happening when we were just following this Ampere's circuital law when your capacitor was charging, and right now when we are bringing this expression ID, what is happening right now? Okay. So now you can see that there is no interruption in current flow at all. Okay. So the general form of Ampere's circuital law becomes, that means after correcting this particular Ampere's circuital law, since it has some limitations we have seen, so after bringing this Maxwell's constant, that means the Maxwell's expression, into the Ampere's circular law. So the rectified Ampere's circular law becomes, I will write the Ampere's rectified equation law in the board, just a minute. Alright. So what is your rectified form of Ampere's circular law? Writing the same thing here. Which is equal that means the line integral of this magnetic field and this dl, the product of them, is equal to, I will explain once again, mu naught I plus mu naught epsilon naught del phi E by del T. Okay. So this is this particular equation, that means equation number 4. We will check out the equation number, students. I think this will be your equation number 4. So this particular equation number 4 is known as your Ampere-Maxwell law. Ampere, I am writing in short, but in your exam I will write the full name, Ampere-Maxwell law. Alright. So basically this rectification of Ampere's circular law is more or less done. So students, from Faraday's law, if you just remember Faraday's law that you have studied in electromagnetic induction chapter, it is obtained that the rate of change of magnetic flux will create an electric field. Clear? That means if the magnetic flux change with respect to time, it will obviously give rise to some electric field. Clear? Similarly, from this particular law, this Ampere-Maxwell law, we can see that an electric field varying with time may set up an magnetic field, isn't it? That means when the electric field will vary, isn't it? When the electric field will vary with respect to time, it will give rise to some magnetic field. Clear? Okay. So in other words, this concept of displacement current develops an important connection between the varying electric field and the magnetic field. Okay, that means this particular equation, from this equation you can see that this displacement current, develops the connection between the electric field as well as the magnetic field.